start that. Make sure it's recording. Good. Make sure this is on. Charging. All right. So last week we finished chapter 9, which I think was just on similar triangles, and seeing how no one but Mark has finished that material, chances are you don't have questions on the homework, or do you? Are there homework problems that you may try to get questions on?
Totally not.
Totally not. So we'll just move on with material to chapter 10?
Yes.
All right. Starting chapter 10. Chapter 10, we introduce area. And we're going to start out talking about area very similar to the way that we start out talking about length. So when we start out talking about length, well, the idea that we have in mind is we measure length in terms of some unit, right?
Mm-hmm.
So I come along and I say that this right here, this unit, I may call 1 inch. And so I want to talk about the length of this segment. And I count off how many inches I can get. And then I eventually get past it, right? So I would say this is 1, 2, 3, 4, 5, 6 inches, 6 point, and then I would like zoom in on that piece. Here's the point I'm trying to get to. And then I start counting tenths of inches, right? And then I would count 1, 2, 3, 4, 5, whatever. So I would say, oh, that was 1, 2, 3, 4. And then I zoom in on that segment and do it again. Over and over again until I get exactly to that point. Right?
Yeah.
And that was how we came up with our idea of the length of something. Well, we have a similar idea when we begin by talking about area. Our similar idea for talking about area is we have a square unit. So I say that this is an inch squared. Now when I have some area, we'll start out talking about rectangles, and I want to know its area, I'm counting how many of those can I fit inside this thing. And maybe I get up to there, right? And I fit that. I know that this is way off, but let's pretend I got 6, and then I've got this little piece left. Then what can I do? I can take a 1/10 by a 1/10 inch, little square there, and then I can start tiling this with those 1/10 inches. And I can keep going like that until I tile the whole thing. And I can count all those. And I can count this is 6 inches, and I can count how many hundredths of an inch, and then keep on going that way, right? So that's some intuition for how we begin area. We start out by counting area. We count how many little squares we can use. Now, a lot of the theorems that we're going to come across in this chapter, you need calculus to prove. And so the author just kind of states the theorems. But he states the theorems, but he doesn't prove the theorems because you need calculus to prove them. So we're basically treating them like postulates. The only reason he's calling them theorems rather than postulates is he's saying, look, in calculus you can prove this, so we're going to call it a theorem. We're just not going to prove it, and you're just going to take our word for it that we have a proof of this theorem. Okay? And so there's 3 main ideas that we're going to assume. One of the things that we're going to assume is that if I have a square, and it is length x, I'm going to assume that the area of this square is x squared. That's one of the assumptions I'm going to make. Another assumption I'm going to make is that if I have some weird shape that I'm trying to figure out the area of it, then I can figure out the area by splitting it into smaller polygons. So in other words, I can find first the area of this thing, then the area of this thing, and add the 2 areas together. So if this thing has an area of A1 and this thing has an area of A2, then the total area of the whole thing is equal to A1 plus A2. Both these should be pretty intuitive for you. So they're simple ideas, but the proofs of them aren't that simple. And so they're stated as theorems in the book. This isn't a theorem in the book. I'm going to prove the one they say is a theorem in the book. I'll talk about that when we get to it. But we can use this instead of what the author does. This is the better place to start. So we have this one. We have this one. The final assumption that we're going to make for area is that congruent triangles have equal area. Okay?
Mhm.
So if I got this triangle here, and I've got this triangle here, and I know that that side is the same as that side is the same as that side, and that side is the same as that side, so we've got congruent triangles, then I'm going to assume that the area of this and the area of this are equal. Which, once again, should make pretty good intuitive sense. Now, small historical note, going back to Euclid and the way that the Greeks talk about these things. When we talk about area, we are talking about a number. The same way that when we were talking about length, we were talking about a number. The Greeks didn't have numbers in their geometry, the same way that we do. So they wouldn't show that two things have the same area by calculating this one's area, getting a number, calculating this one's area, getting a number, and then showing that those two things are the same number. That's not the way the Greeks would have done it. And I'll show you an example of how the Greeks talk about area when we do the Pythagorean Theorem. So when the Greeks used the word equal, when they were talking about equal, they meant have the same area. So the Greeks, in Greek geometry, it's possible to have square equals this triangle. When I say square equals this triangle, I would say it when this and this have the exact same area. And that's how the element uses the word equal. It means same area in the context of two-dimensional figures like this. So a small historical note, and that's because they didn't have area as a number. They didn't have area in our head. We think about area, we think about number. They didn't have a number to represent what this thing is, but they're saying this thing and this thing are equal in the sense that they occupy the same amount of space. They just didn't have a number for that. Does that make sense? So we'll see an example of that when we prove the Pythagorean Theorem again. I guess none of you were there when we proved it except for Mark. But we'll prove it the way that the Greeks would have proved it because they couldn't, because they didn't have these numbers the way that we have numbers. Okay. So these are our three big assumptions. This, this, and this. Now I don't know how these relate to theorems in the book. I'll try to go through the book in the same order and then I'll introduce them as they come up. So let's see. In the book, you know what we have for area. So theorem 10.1 in the book is that the area of a rectangle whose sides have length L and W is L times W. Now that's one that they don't prove. We're going to prove that using this. Okay? Do you understand my three assumptions here? Maybe somehow have a way of writing them out. One, if we have x, then a equals x squared. Two, if we have some funny shape with a1 and a2, then a equals a1 plus a2. And then three, if triangle with a1 is congruent to triangle with a2, then we have a1 equals a2. All right, is that clear enough way to write down our three assumptions? Okay, so that's what we'll be using in this class for this chapter. And then let's do the first proof. This proof isn't in the book because the author wanted you to use this postulate. I may use this instead. So, theorem 10.1. If the length and width of a rectangle are L and W, comma, then the area is L times W. Okay? So maybe I won't bother writing out all the words for these proofs because they're very picture, and once you see the picture, I think you kind of see the proof. So what I'm going to do is I'm going to construct a square whose side lengths are L plus W. With me? So we have a square here, and this is These side lengths are L plus W. Let me see. Let me try and remember exactly how I wanted this. Let me put some points on here. So let's. Sorry, I keep bouncing back and forth in my thinking. L, W, W, L. Is that how I want it? So we have this, this. Okay, perfect. And then, that doesn't line up very good. Shift that point low. And then I'm trying to find the area of this rectangle, or this rectangle. Notice that this rectangle has length L and width W, okay? And I only have a postulate so far that I can talk about squares to get the area. So that's why my first thought is I need to reinterpret this question in terms of a square that has my area in it somehow, right? So what's the area of this whole square? Tell me exactly what to write.
That would be parentheses of L plus W. And then
L plus W squared, right? Right here, that's using this. The area of a square is this distance times this distance, or in other words, this distance squared, because this distance and this distance are the same. Do you see that L? Maybe I should specify that. L is going from here to here, and then W is going from here to here. So this whole distance is L plus W. So we're taking L plus W and we're squaring it, which is equal to L squared plus 2LW plus W squared, right?
Why do you have to go to?
Oh my goodness.
How many LWs are there?
A plus B squared is equal to A plus B times A plus B is equal to A times A squared, A times B, AB, B times A,
That.
BA, B times B, B squared is equal to, combine those two like terms, A squared plus 2AB plus B squared.
Okay, so it works with A's and B's.
I forget you guys haven't done algebra. You good with that? Does every step I took make sense? You know the distributive property? Okay. So this is equal to this, right? Now, using this thing, we know that the area of this whole thing is the sums of the areas of the individual parts. I know that the area of this part is L squared, and I know that the area of this part is W squared. So the area of this plus this has to be 2LW, right? Now there's one more step that we need. So I know that the area, let's call this A1 and A2. I know that A1 plus A2 has to equal 2LW. Right? And then I'm going to have to use this one to show that so I've split this into two triangles, show that all the triangles are congruent. Therefore, each of those triangles is 1/4 of this, and two of them together is half this. Do you see what I'm saying?
Yes.
So, kind of just drawing all over my picture here. So we would think about splitting that into two triangles and splitting this into two triangles. We know that this triangle is congruent to this triangle by side, angle, side. All the angles are right angles, right? So I know this triangle is congruent to this triangle, is congruent to this triangle, is congruent to this triangle. So all these triangles are equal. Sorry, congruent, not equal. All these triangles are congruent. Therefore, all these triangles have equal area, right? And using this one once again, the sums of the areas of these four things has to be, the sums of the area of these two things has to be all this. So each triangle has 1/4 this, So A1 is equal to half that LW, and A2 is equal to half that LW. And so the area of a triangle is length times width. Do you see all the logic there?
Yeah.
Were there any weird steps? Do you think you could redo that? Okay. Which of you wants to do it? You all nodded.
I will.
You will?
Yeah.
Okay, so not Leah.
Okay, I will.
All right, come up. No, you can stay there. All right, just want to make sure you meant it. Now, so that proves theorem 1. Theorem 1, he wanted you to take his postulate. I think that this is a better place to begin. So he doesn't start there, he doesn't even bother with that. That's just a special case of theorem 1 in his mind. So next, that was theorem 10.1. Next, theorem 10.2 is congruent triangles have equal area. He doesn't prove it, so he just takes it as a postulate. So theorem 10.2 is just that, which we already talked about. My book keeps turning pages. And then theorem 10.3 is this one right here. So 10.1 was rectangles, 10.2 was this, 10.3 was this. So we've covered the first 3 theorems, which are kind of like the postulates for this chapter that we're going to use. So now let's do theorem 10.4. Theorem 10.4. That's not how I'm doing it. Dash 10.4. Theorem 10.4. If A and B are lengths of the legs of a right triangle, the area of the triangle is 1/2 AB. If A, B are lengths of the legs of a right triangle, comma, the area is 1/2 AB. You remember what the legs of a right triangle are?
Yeah.
What are they? They're the sides that aren't the hypotenuse, or the sides adjacent to the right angle, however you want to think about it. So if we have some right triangle, the legs are these things, A, B. So if the lengths of the legs are A and B, we need to prove that the area of this thing is 1/2 AB. How are we going to do that? Form a rectangle, right? So we form this rectangle. What's the area of the rectangle?
A times B.
A times B, we just proved that. And then this triangle is congruent to this triangle. So these two things have the same area. The sums of the areas gives us the total area. So each of these rectangles has half the area. Do we need to write that out, or is that pretty obvious?
Pretty obvious.
That's a good one? You got that? All right. So that's theorem 10.4. Theorem 10.5. Whoa, I closed my book. Hope I didn't take out my bookmark.
185.
8.5.
185.
Oh, that's the page. Theorem 10.5. The area of a parallelogram is equal to the product of its base and its height. Okay. Theorem 10.5. The area of a parallelogram. Am I doing that right? Parallelogram. Thank you. I knew that felt weird.
Wait.
No.
It's A. No,
It's
it's
an
O. It says it right there.
Oh.
Parallelogram.
I think she's right.
Parallelogram. Oh, parallelogram.
Just feels weird. write a word 100 times and then one time you go right, it feels weird. Alright. The area of a parallelogram is what's the verbiage it uses?
Equal to the product of.
Is equal to the product of its base and height. Okay, so let's prove that. Start with a picture of a parallelogram. Do you remember what a parallelogram is? Both the sides are parallel to each other.
Yeah.
And then one of our little lemmas we did last time was that the opposite sides of a parallelogram are congruent to each other. So we start out with this parallelogram. Maybe we'll start labeling points. A, B, C, D. So there's our parallelogram. And then we're going to construct the rectangle that we get from dropping a perpendicular down from there, extending that, perpendicular up, extending that. And we get this shape right here, right? Maybe rather than points, it would be better to have just numbers for lengths to talk about this. So we'll call this length x, well, b for base, I guess, because that's what's referenced up there. So that's base, that's also the same, opposite sides of a parallelogram are congruent. We'll call this missing distance over here x, and we'll call this the height. And that's what's meant by the height of a parallelogram, by the way. Pick from whatever you call its base, shoot up a perpendicular, and then where it reaches the top, the line through the top is its height. Does that make sense?
Mm-hmm. Yep.
Okay. All right. So that's the figure that we're talking about, and we're trying to prove that the area of this thing is the base times the height. Now, first off, we're obviously going to talk about the area of this whole thing. So what's the area of the whole rectangle?
It's b plus x times h.
B plus x times h, right? And then, what's the area of, and remember that these are right angles because for the height we shoot up perpendiculars. What's the area of this?
Half of xh.
1/2 xh. So this is 1/2 xh, and this is 1/2 xh, right?
Together they make one full x.
And so we'll call this thing A. So A is equal to the whole area minus those two pieces,
Subtract xh.
right?
Yeah.
Which is equal to, distribute this out, we get a BH plus an XH minus an XH, which equals BH. And we're done. You see that? The area of the parallelogram we're looking for is equal to the area of the whole thing minus the area of these two pieces. So the area of that parallelogram, and then you just do the algebra. Good?
You guys already know that.
Oh, I knew it, but I
No matter how far you stretch it, you stretch that to China.
Yeah.
It'll be the same area.
It's something that's
No, it wouldn't.
not obvious.
It'd be the same formula, not the same area.
Same area.
Same area.
That and another one. 4 billion.
This
times
parallelogram
Same area.
right here,
Obviously, a bigger height.
that parallelogram is the exact same as this parallelogram. They both have the same area. That's what that formula just says. And I can keep stretching that thing as far as I want. I don't increase the area.
Like 4 miles.
It should do. No, you're not increasing the height.
Oh,
We
it's
just
curved.
proved that the area of that thing is this thing's base times however tall this thing is.
There's no
It's
x
this
in
thing's
that.
base
Yeah.
times however tall this thing is.
You can stretch it.
You see how it's not obvious?
Taller, you can stretch it.
It's a pretty cool result. That's always true.
We don't care what that x is.
Yeah, however far this x is, this stretching
I'm
distance.
saying if you change the size of it, it will change its area.
Okay. What do you mean by changing the size?
We're
If
saying
you change it-
stretch, not tall, stretch that way.
Yeah.
You don't change the
He's
height of the
saying-
base.
Imagine I grabbed right here and kept pulling this way.
Oh, yeah.
And kept pulling. And I kept walking all the way to China, is what he's saying.
Yes.
Now,
that makes
China
sense.
involves some sort of curvature, but if I went on a straight projection, a billion light years out that way, stretching this thing,
I was saying
it
the
still
other
has the
side.
same area. Right?
Yes, but if you were to change its height, then what change the area would
Yeah.
it?
If you
Okay.
change the height or the base, you change the area. The cool part is it doesn't matter what this x is.
Yeah.
It doesn't matter how much you share it. It still has the same area. Which is not obvious from looking at it. That this thing and this thing have the same area.
Yeah, that's weird.
It's weird, right? But there you go. The x's go out. Cool. All right. So that's theorem 510. Theorem, do you guys just want to read these to me instead of me having to reopen my book?
10-6.
Yeah. Theorem 10.6, what is it?
The area.
Oh, make sure you didn't skip any definitions along the way.
You did it.
Okay.
Okay, 10-6. The area of a triangle is given.
Okay.
By the formula A equals 1/2 B times H.
So area of a triangle is, we don't need the A equals, is 1/2 base times height. And there's two ways that we could do this proof. So we already proved this for the case of the right triangle. And there's two ways that we could do this proof. For any triangle that you draw, no matter how crazy, that's a pretty crazy one, right? If I pick the longest side and then construct a rectangle using that side, that's not a rectangle. Maybe more like that. And then you, from this point, drop down a vertical. Then you get this triangle is congruent to this triangle, this triangle is congruent to this triangle.
1/2 the.
And so this triangle is half this rectangle, this triangle is half this rectangle. And so it's 1/2 where this is base and then this is height, right? 1/2 base times height. That's one way to do it. There's another way to do it.
Parallelogram.
Yeah, parallelograms. How'd you know?
Just assuming off of what we just did.
So draw some triangle, and then I'm gonna flip the triangle this way, and then flip it that way. Okay? So maybe to show you, I'll draw one side black. So I'm gonna flip it up this way, and then flip it this way and redraw it. So that my black side is gonna come out right here. Right?
Yeah.
And then this side's still touching this side, and then my other blue side is up here. So when you do that, you get a parallelogram. Here's our base. Our height is this thing. We know that the area of a parallelogram is base times height, and our triangle is half the parallelogram, because it's congruent to this triangle we drew over here. Now, there might be, how do we know that when I draw my triangles like that this is a parallelogram? Maybe that's a question we ought to consider for a second.
Well, if
Because you know that this side's congruent to this side, you know this side's congruent to that side, and then this side's congruent to this side. How do I know it's a parallelogram?
Well, you have congruent triangles, and then therefore you say the alternate interior angles are congruent.
Perfect, that's exactly how you'd say it. You would say, look, this angle is congruent to this angle, and therefore, these two lines are parallel, and there's a transversal between them. If you extend this, and you think about extending that. So since alternate interior angles are congruent, then these two lines are parallel. Right? And then we can do the same thing for thinking about these two lines. So it's a parallelogram. So you might need to argue a little bit that that is in fact a parallelogram. And then once you have that's a parallelogram, the area of a parallelogram is base times height, where here's our base, here's our height. And then so this triangle makes up half the area. So it's half the base times the height. So another way you get the exact same formula. Okay, so that's theorem 10.6. What's next? Theorem 10.7 or is it definition? What is theorem 10.7?
For every right triangle. Oh, it's Pythagorean theorem.
Oh, the next one's the Pythagorean theorem. Okay, so now I'm going to show you the Pythagorean theorem the way that the Greeks did it. So here's Pythagorean theorem the way that the Greeks did it. We don't need to write out the theorem. You know the Pythagorean theorem, right? Okay. What's the Pythagorean theorem? If you say a squared plus b squared equals c squared, I'm going to throw this marker at you.
It's if there's a right triangle,
If there's a right triangle,
then
Then they square.
no, and C is the hypotenuse. Then, and the two base legs are A and B, then A squared plus B squared equals C squared.
wonderful, that works. The sum of the squares of the base of the legs is equal to the square of the hypotenuse, right? So that's what we're going to prove, and now I'm going to show you the way that the Greeks would have done it. Because remember, the Greeks didn't have a way of getting like a number as the area and then using that. So they would say, the triangle we're thinking about, I don't know if I'm going to draw this right now. Hopefully that somehow makes sense with our picture. Maybe it's in a little bit. Here's A, here's B, here's C for our triangle, right? So we have a right triangle, we're going to call that length A, that length B, the hypotenuse C. And I'm trying to prove that A squared plus B squared equals C squared. That's what I'm trying to prove. So I'm going to construct a square over here, where this is A, this is B. That's A, that's B, sorry, that's not very good.
BA.
No, I'm not doing it the way the book does it. Very similar to what we just barely did for proving rectangles. So this area right here is A squared. This area right here is B squared. This is AB, and this is AB, right? And then I'm going to make another rectangle, well, square. And this time, I'm going to do A, B, A, B, A, B. Sorry, I'm not being very consistent, but I think you'll get the picture. So A, B, A, B, A, B, A, B, and then I'm going to connect like this. The point is that each of these triangles is this triangle, right? Is congruent to it. So this distance to C, this distance to C, this distance to C, this distance to C. And we also know that this right here is a right angle. How do I know that's a right angle? I know that this
And that.
is congruent to this. I know that this and this are congruent. What is that plus that plus that?
Straight angle.
What is that plus that plus that?
Straight angle.
So that angle has to be congruent to that angle. Right?
Yeah.
Okay. So that's a right angle, and this is C, and this is C. Right? What's the area of this thing over here?
A plus B.
A squared plus 2AB plus B squared. What's the area of this thing over here? The one right here is c squared, right?
Yeah.
And then this is 1/2 AB, 1/2 AB, 1/2 AB, 1/2 AB.
So 2AB.
So 2AB plus c squared.
Right.
So A squared plus B squared equals.
So that has to be equal to that because those are both the same area. Because they're both the area of the square with side lengths a plus b. You see it?
Yeah.
What's up? Up. So, a squared plus b squared equals c squared. Now the Greeks didn't have the algebra that we have here to do this, so it's much more wordy. But this is the idea that they used to prove it. Pretty cool, huh? Count the exact same area two different ways. So there's a Pythagorean theorem. What was that? 10-7? 10-7. Now, the way that the author talks about it is he just looks at this directly, just this square. And he says that this distance is a plus, this area of this square right here is a plus b squared. That's the area of the square, right? Which is using this postulate. And then, looking at our picture, counting up the individual areas using this postulate, we got c squared plus 2ab. And then he just does the algebra on this. And he gets a squared plus 2ab plus b squared is equal to c squared plus 2ab. And then he goes from there. But the Greeks didn't have the algebra, so they had to come up with two pictures representing the same area different ways. And then cross out identical areas. So the way that they would have done it is show that those two triangles are the same as big as those two, and those two are the same big as those two. So those cancel out, so you have those two areas in that area are the same. But we just had a nice algebra to capture that same idea. Right? Okay, so there's Pythagorean theorem. Pretty cool, pretty cool. Now let's move on to construction problem. The construction problem is, if I give you any quadrilateral, I want you to construct a triangle that has the same area. What's a quadrilateral? Four-sided. Maybe it has to be convex. I don't know. Does it have to be convex?
That's hard.
There are it is interesting to note that it is possible to construct a triangle whose area is equal to the area of any given polygon. We indicate this procedure constructing a triangle equal in area to a quadrilateral. So they don't specify it as convex or not. Alright, so let's draw some messy quadrilateral, but I'll also draw it so that my picture doesn't get too messy. So we've got some point like that, some point like that, and then we'll make, I don't want to slant too much there, but that should give us enough space.
Okay.
So some random quadrilateral, there we go, A, B, C, D. My goal is to construct a triangle that has the exact same area as that thing. Understand the problem? So, one of the things I'm going to do is extend this line. I'm going to take this line, and then I'm going to draw a line through this point parallel to this line. And the way I can do that is just construct a perpendicular line here to this point. Remember, we did that. Given a point and a line, construct a perpendicular line that goes through the point. Remember doing that last time when we did it? So we know how to construct a perpendicular line to this that goes through that point, and then construct another perpendicular one going this way. And that's how you get your parallel line. You understand how to construct that parallel line? I do perpendicular to this going through that point, then I do perpendicular to that going through that point. That gives me this parallel to this. Okay? So, with this we have this and this are parallel. Now, my claim is that this triangle going from this point E here has the same area, although I did not draw it correctly. Huh?
What in the world?
Hold on. If I draw my picture better, then it will show better. Let me draw my picture better, because my parallel line was not even close to parallel. Because my parallel line should be like meeting somewhere over here.
That's a little better.
Yeah, that's a little better. Makes it a little bit more believable. So, if I drew my picture perfect, it'd be a lot more believable. But we'll prove it, so you don't have to worry about it being believable by a picture. But anyways, so my claim is that this triangle, when I connect this point here, has the same area as the quadrilateral. So maybe I'll kind of I'll write out steps for this one so that you can see my thinking as we go. So prove area of, let's pretend that we start out with this picture, so I don't have to say construct this, construct that, whatever. Prove that the area of triangle ABE prove area of that is equal to area of quadrilateral ABCD. All right. 1. Observe that the area, oh, I keep doing capital A every time I write area. Area of, let's go over the big picture and then we'll write it out to see it happening, because it's kind of a messy picture. Here's my big idea. So I'm showing that the area of ABCD, that quadrilateral, is equal to the area of triangle ABE, right? The way I'm going to show that is, notice that both those pictures have this area inside of them. Right? So I need to show that this triangle, right here, so maybe I need to label this point, F is the intersection of those. This triangle, BFC, has the same area as this triangle, FDE. Right? That's right. So if this little triangle down here has the same area as this triangle up here, then this whole shape has the same area as this whole shape.
Right.
This whole triangle, right? So to show that this piece is the same as this piece, I'm actually going to show that this triangle, BDE, has the same area as this triangle, BDC, and then they both have this area in common. So then we take away the same amount of area from both of them, and so the remainders have to also be equal. So then showing that these two triangles are the same is just showing that they have the same base and they have the same height, which they do.
Which two triangles?
How do they have the same height?
The triangle, this triangle, and this triangle have the same base and the same height.
Where's their height?
Their height is the distance from this parallel line to this parallel line.
Why?
So let me draw a secondary picture real quick. So imagine I have two parallel lines. Let me use blue. Imagine I have two parallel lines. Okay? And I have one triangle drawn like this, and I have another triangle drawn like this. They both have the same base, and they both have the same height. Remember, the height is drawn a perpendicular up.
Oh, so it's
But that's
the
not
BC
how it
and
is.
the DE.
It is. I have these two parallel lines with the same base. So they go from this parallel line with a base, and then their vertex is on the other parallel line. It's this exact same picture. I tried to draw it kind of similar,
Okay.
except this one's flipped the other way.
Longer.
No, I drew it pretty good. It's just, do you see it?
Yeah.
Do you see it? Okay, let's start over here.
No, what two triangles are you talking about?
I outlined it in pink.
You were turning them back to
and
her
BDC.
16.
Oh, you can't see what I'm talking about?
No, I'm just trying.
This triangle, B, D, E, that triangle right there, has this base for its base, and has the distance from this parallel line to this parallel line for its height, right? And then this triangle, B, D, C, has for its base this base, and then the distance from this parallel line to this parallel line for its height.
Yeah.
So those two triangles have the same area. So get rid of that middle part, and this have the same area. And then add that whole part, and so that triangle and that quadrilateral have the same area.
Right.
You see all that?
Yeah.
Kind of messy, huh? Alright. So let's go back and erase all this and pretend that we start with a picture, something like, doesn't really matter how we draw it. So we'll call that A, B, C, D. We'll extend this line, try and leave blue as like the quadrilateral. Extend that line. Do my parallels dotted with blue, I guess. So I'm going to have a line from here to here. And I'm going to have its parallel up there. So let me know that this line is parallel to this line. Right? Label that point E. Finally, what color should I use for this last triangle? Do pink. The triangle that we get from connecting these 2 points, triangle BAE, is the triangle that has equal area to our quadrilateral. That's what we're proving. So let's pretend we start out with this picture and we're trying to prove that ABE is congruent to ABCD.
You can label that.
F. Perfect. And F is the intersection of those. We just need F so we can talk about this interior triangle. Okay. So first off, observe that the area of triangle ABCD is equal to area of triangle ABE if, so that area of the quadrilateral and the area of the triangle are equal if this triangle BFC has the same area as triangle FDE. Because we just subtracted away that part of it, right? If the area of triangle BCF is equal to the area of triangle DEF. What did you say? Def. Triangle def. Book versus def. Okay. Book. So, next thing is going to say these two triangles have the same area if triangle BDE has the same area as triangle BDC. Right? Because then you're adding this little triangle to this one, and you're adding this little triangle to this one. Does that make sense? Mrs. Sleepy? Don't nap in my class. Don't throw stuff at me. You missed so bad the camera didn't even catch it. Jeez. All right. So, observe that the area of triangle book is equal to the area of triangle def if the area of triangle BDE, is that the one I want to talk about first? Let's see, which one was BCF? BCF was that one, so I'm going to first do BDC and then the other one. Triangle BDC, if the area of triangle BDC is equal to the area of triangle, which one was it? BDE. Three, observe that since lines or line, observe that since BD is parallel to CE, comma, triangles observe that since that is parallel to that, then triangle BDC, is that the one I do first? Triangle BDC and triangle, what was the other one? BDE have the same height when considering BD their base. So if we view BD as a base of both those triangles, then they have the same height. Or maybe I should have said the altitude from point C is equal to the altitude from point E. That's probably a better way to say that.
Yeah, but where do you take the altitude
The definition of altitude for any triangle is, so if I have some crazy triangle like that, then in the definition you have to extend that line to parallel, and then you drop, we say drop, but really it's construct a perpendicular up to that point, and then the length of that is the altitude.
So you're saying instead of saying have the same height,
Yeah.
say.
I don't like talking about height, we should really be talking about altitudes. But the length of the altitude is the height.
Oh, okay, I get that.
The altitude of a vertice, if we're talking about the altitude from A of that triangle, it's just the line that you get from dropping one down that's perpendicular to the opposite side. And you only go until it meets that line. So that's the altitude of this triangle. Does that make sense? Anyways, I think you understand why I wrote it there, so it's good enough. 4. Then, triangle ABC has the same area. As triangle BDE. Right? Are you good with making the leap from here to here? If they have the same height when considering BD their base, then they have the same area.
Yeah.
And we already said the parallelogram, or not the parallelogram, the quadrilateral has the same area as this triangle if this triangle has the same area as this triangle. Oh, sorry. We started out with the quadrilateral has the same area as this triangle if,
No.
No, not that.
Not that one.
ABE.
oh, thank you, as this triangle, if this triangle up here has the same area as this triangle, and this triangle has the same area as this triangle, if this triangle has the same area as this triangle, which it does.
Yeah.
So we're done.
Yep.
Good?
Great.
You gonna rage again? Alright.
That was a lot.
I was looking at Laura. Okay, so that was that construction, and I think that finishes chapter 10. Pretty easy chapter, huh?
Yep.
Already. Wow. Now we gotta get into circles and regular polygons. Oh, there was an area of one thing on there that I see in the review that we didn't do. We must have missed it. We didn't do the area of a trapezoid. The review of chapter 10. Just number 1.
Area chapter.
Yeah. So let's do area of a trapezoid, because I guess I must have skipped that somewhere. And it's in the review. What is the area of a trapezoid?
It's just a parallelogram with two triangles.
Two triangles.
What is it?
It's a special parallelogram.
I think I see how you're doing it.
Rectangle.
Yeah. Okay.
More
The area of
triangles, the
trapezoid.
better.
Yeah, so let's figure out what the area of a trapezoid is real quick.
You draw 3 triangles.
Two of those make one
Now I'm just
parallelogram.
curious. So a trapezoid has 2 sides parallel, and the other 2 sides aren't necessarily parallel. So there's a trapezoid. Okay? We're trying to figure out what the area of that thing is. Now you said draw 3 triangles.
I
So-
can see it.
I know how to draw 2.
One upside
I'm gonna
down.
draw
Draw.
3.
One upside down.
Look. No, the
Draw
left.
and Psycho Aquarius, like.
I see what she's saying, but that's dumb. The
I
top
don't-
left vertex, you draw a parallel. Because you can split that parallelogram into different triangles.
Okay. So first thing he said is let's draw a parallel line here. So now we've got this is parallel to this. Maybe put some numbers on here now. The typical way that they talk about the area of a trapezoid is in terms of this base and this base. So I'll call this B and this B prime. The book probably does something like that as well. And then, just so we have it, let's make a rectangle real quick so that we can talk about the height of this thing. Right?
Yeah.
H. Okay. So, what's the area of the overall trapezoid?
B.
What's the area of this part?
B. B prime times H.
B prime times H. And what's the area of this part?
B times H.
1/2 B times H.
1/2 B times H.
Why is it's right? Oh, I didn't realize
So yeah. So the area of the whole thing is equal to.
that.
Oh, wait a second. No, I can't believe I even wrote that. The area of this triangle is not 1/2.
Oh yeah, that's wrong.
1/2 base times height? No.
No, it's not.
So what's the area of that triangle? Sorry, we still have a b down here.
It
Which
would
is
be b subtract b prime.
b subtract b prime. So this is 1/2 b minus b prime h, right?
Right.
Right? If this whole distance is b, and this distance is b prime, then this distance is b minus b prime.
Oh, I see.
So base is b minus b prime, height is height, and 1/2 the base times the height. That's a minus sign, that's not a times sign. This is a minus. Right? So now the total area is equal to b prime h plus 1/2 b minus b prime h. Now I know you guys struggle with algebra, so let me finish computing this out for you. We get b prime h plus 1/2 b h minus 1/2 b prime h. Right? Because if you carry the 7, and that's what you get. Good? Now we have 1/2 b prime h and we have a b prime h. What do I get when I combine those two?
Half b prime h.
1/2 b prime h. So combining these two, we get 1/2 b prime h and plus 1/2 b h. Now what can I factor out?
That.
That?
How could you? Oh,
That's it.
Oh, we're done? That's the answer you would give for the area?
You can't add them, they're not like terms.
But can you factor anything?
Can you subtract?
Have you heard that word before? Yeah, can you subtract anything from them?
1/2.
No, can't subtract. No, you can't subtract 1/2. You can't have 1/2 of 5. Oh, and then minus 1/2 from it real quick. And that equals
Okay,
5.
Okay.
Shut up.
Okay.
No, 1/2 h parentheses b prime b plus b prime.
There you
h.
go.
So we can factor
Is equal to 1/2 h b prime plus b, which is a formula that you'll probably see. What does it look like? H times b plus b prime over 2. I like this better. Now, the reason that they do it the way that they do it, another way that you might commonly see it to help your intuition, is it's equal to h times b plus b prime over 2. Now, why does this help your intuition to think about it this way? They're saying take the average of these two bases and multiply it by the height.
Oh, yeah.
So that way of thinking about it might help your intuition, but I think that that's the prettiest way to write it. I'm all about what's beautiful. Look at those factored out terms.
Wow.
All right. So that was the area of a trapezoid. I don't know where that came up in the book, in the chapter, but we must have skipped it because it's in the review.
And that's fine.
Oh, it's an exercise?
And then exercise period.
Well, all right. So I guess you guys were supposed to prove that, not me.
What?
What I just wrote up.
That's okay, you did that.
All right. So now we get to talk about circles and regular polygons. What is a circle? No, those are two
No
hands.
angles
The
and
point
no.
and the radius and all the radiuses. All the radiuses.
All the radiuses.
No, it's like
How many radiuses does a circle have?
Infinity.
So if I say draw a circle with radius 3 centered at this point, that's only one radius. I told you.
yeah, but it's all the ones at the same distance of the radius around that point.
Say that again, but now say it exact. What is a circle? First off, it's a set of points. Now which points?
Same radius.
The same radius points?
Same distance from the center.
As a radius.
Yeah.
So select a point, call it the center.
Yes.
A circle is a set of all points whose distance from that point is the radius. So I take all the points whose distance from this point is exactly the radius, and it's the set of all those points, those infinitely many points that we're talking about. That's what the circle is. It's a set of infinitely many points, exactly our distance from that point. any point I can find in the whole plane that's r distance away from that point is part of my circle. If there's a point right here that's exactly r distance from there, it's part of my circle.
Wormholes.
Yeah.
Don't get mad there, Donnie.
Alright, you understand what a circle is?
Yes.
Okay. What is a regular polygon?
It is a polygon with that is equilateral and equilateral.
Perfect. That's exactly what it is. It's an equal angular, equilateral polygon. What's equal angular?
Equal angles.
And what's equilateral?
Equal sides.
Yeah. So if all the side lengths and all the angles are congruent, then you have a
So
regular.
it's a square.
Well, that's a four-sided one. I can have a regular pentagon. I can have a regular hexagon. I can have a regular heptagon. I can have a regular octagon. I can have a regular nonagon. I can have a regular decagon.
Lastly.
Right? Okay. So, that's what a regular... So that you can understand what the chapter heading says, we're talking about circles and regular polygons. We're talking about those two things. Okay. Definition 1. A regular polygon is inscribed in a circle if all the vertices of the polygon are on the circle. We may also say that the circle circumscribes the polygon. So let's make sense of that. I take some regular polygon, we'll use a square I guess, but it doesn't matter what we use. I say that it is inscribed in a circle if I have a circle that goes through all of its vertices. So it has 4 vertices. If all those 4 vertices are on a circle, then we say it is inscribed in the circle. If one of those vertices wasn't on the circle, then it is not inscribed in a circle. So that circle, well, there's 2 different ways that we say it. The circle circumscribes the square, or the square is inscribed in the circle. So let me read the definition again one more time verbatim so that you can see it with this picture. A regular polygon is inscribed in a circle if all the vertices of the polygon are on the circle. We also say that the circle circumscribes the polygon. Does that definition make sense?
Yep.
Okay.
Oh, it's circumference.
The circle circumscribes this thing, or this thing is inscribed the circle. Oh, did we already have a theorem too? Theorem. There's exactly one circle circumscribing a given triangle. So let's do that. Theorem 11.1. There is one and only one circle that circumscribes a given triangle. Something to that effect.
Why can I not be two?
Huh?
Okay, wait 1 second.
So if I draw some triangle, there is one and only one circle that you can draw that has those 3 points on the circle.
That's blowing my mind.
So let's go through how we might prove this. So first off, we need to prove that there is one. And then secondly, we need to show that if there were another one, it's really the same circle. Okay? Maybe make sure that all the side lengths are very different so that we can see it the best we can. I don't know that I'll need points to talk about this. Not sure how I'm going to prove it yet. But we'll put those on there. Okay. So let me think what I am going to want to do. Prove this. I'm thinking we go to the midpoint here and we construct a perpendicular bisector. We go to the midpoint here, we construct a perpendicular bisector. And then we call that point where they meet O. My thinking for that is now, first off, let me make sure you understand what I'm saying. Do you understand what I mean by, say, draw a perpendicular bisector for this segment and this segment, mark where they intersect? My claim is going to be that that point where they intersect O is the center of the circle. Okay? So in other words, I'm saying that this point, and this point are all the same distance away from that point. So if you draw a circle with this as its radius, it's going to go through all three of those points. You see what I'm saying? Okay. So we're going to be considering this length, and this length. Now, first off, it's a perpendicular bisector, so I know that this side is the same long as this side, because it bisects, it splits it in two. So that side's the same long as that side. And then it's perpendicular, so we got right angle and right angle, right? And then this side length is the same. So basically, ABO is an isosceles triangle is what I was getting at. You see that? So this side length is the same long as this side length. Put two ticks because we already used one. Do you see that? By side angle side, these two triangles are congruent. Therefore, this big triangle is an isosceles triangle because these two side lengths are congruent. Right? Okay, same exact argument for this triangle down here. So that's now the same long as that. So this point, and this point are all the same far from that point. Therefore, if I draw a circle with radius OA, then A, B, and C will all be on the circle. So there is at least one circle that goes through all those points. Now, how am I going to say that there's only one circle that goes through all those points? Well, we're going to show that if we have one, then it has to be right here. So now let's think about it in reverse. So let's pretend that I have a circle. Let me try and draw a circle. And it goes through A, B, and C. I'm trying to draw at least a somewhat similar picture. It has some center O. I need to show that if O lies on this thing's perpendicular bisector and this thing's perpendicular bisector, I need to show that O lies on both those perpendicular bisectors, and then it's the same circle. Do you see what I'm saying?
Yes, but I don't see how you do that.
Why would you do that?
Okay. Let's see if I can explain this logic a little better. When I constructed these two perpendicular bisectors, they intersect at a point, right?
Yeah.
They intersect at one and only one point. Two lines only intersect at one point, which is the center of the circle, with this as its radius, right? So now, if I have some random circle that still inscribes those 3 points, so we're still talking about these same 3 points,
Then it's the
Congruent
same.
triangle.
then I'm going to show that if you draw a perpendicular bisector here and a perpendicular bisector here, they intersect that point.
Yeah.
Therefore, they're the same.
And since perpendicular bisectors only intersect at one point, and they intersected at the center of this circle, and if they hit this thing, then those two circles are the same circle. Do you see my thinking there?
Yes.
So now let's reverse think about this. So let's pretend that we had the circle here already.
Erase that inner side, make the picture cleaner.
We just reverse to exactly what we did here. So I'm going to say, well, then this distance is the same as this distance, is the same as this distance, right? So then, wow, that's terrible. then that is the same as that is the same as that. Then I can go to this, drop down its altitude. I can go to this, drop down its altitude. Or not drop down its altitude, sorry, bisect the angle, so that this angle is the same as this angle. Right? And then by side, angle, side, those two triangles are congruent. Therefore, this is the same big as this, and these are right angles. And therefore, that's a perpendicular bisector. Do you see that argument?
Yeah. How do you know it's perpendicular?
Because that angle is congruent to that angle, and together they make a straight angle.
Oh.
So they have to be right angles. Supplementary congruent angles are right angles. It's the definition of right angle. Although it doesn't use the word supplementary, it just says. Does it? Supplementary angles whose supplementary congruent angles whose sum is a straight angle, something like that. Oh, supplementary implies that there's some straight angles. So supplementary congruent angles, that might be its exact definition. Anyways, you see the thinking?
Yes.
So that's how you prove this. Should we walk through that one more time?
No.
We're good? Okay, if we're good, then let's start with the triangle, and you tell me how to find its center.
Oh.
So I'm going to give you a triangle. Okay, come on. Show me where the center of the circle is at. Circumscribe it. How do we find it? Maybe give some points here so you can talk to us as you do it.
You want me to actually do it?
Yep.
Fine.
So perpendicular bisector goes up. So she says find a perpendicular bisector, and she says find a perpendicular bisector. And you're saying that's the center of the circle? How is that the center of the circle?
Yeah, try drawing a circle like that. It's not going to get 8, is it?
What am I doing wrong?
Well, you're saying that's the center of the circle, right?
Yeah.
Okay. How do we know that's the center of the circle? What does it mean for it to be the center of the circle? It has to be the same distance from this point, and this point, right?
Yeah.
So is it? How do you know?
How do we know? Because
So now you need to think about this distance, and this distance. If those distances are the same, then yeah, you found the center of a circle. That circumscribes that triangle. So how do we know that those distances are the same?
okay, so you do this.
Yeah, since those are perpendicular bisectors, and we know that those segments are congruent.
And then there are isosceles triangles.
What are isosceles triangles?
This is an isosceles triangle.
The big one?
Yeah.
How do I know that this half is congruent to this half?
Because the angles.
By what theorem do I know that this triangle is congruent to this triangle?
Side.
What's my other side? I only see side and an angle. We don't know that those are equal. We're trying to prove that those are equal. So we've got this side, that angle.
This side, because
We don't know that these two sides are equal. We're trying to prove that this triangle is congruent to this triangle. We have it by side, angle, side. That side's the same one on both triangles. There you go. And since these two triangles are congruent, then these sides are congruent.
Yeah.
There you go. Wonderful. Great. So I think you got it. And then you just do reverse thinking to show that if you have a circle circumscribing it, then it's those bisectors, right? So I think if you understand one way, showing the other way is pretty easy. Okay, so that was theorem 11.1. Now, what's next? The definition of a theorem. Theorem 11-2. Okay, So theorem 11-1, we showed that if you have a triangle, then there is one and only one circle circumscribing it. Theorem 11-2 is if you have any regular polygon, then there is exactly one circle circumscribing it. Yeah, so instead of any triangle, now it's any regular polygon. Any regular polygon is circumscribed, up to you, circumscribed by exactly one circle. Okay? So now let's start out with a regular polygon inside of a circle. Let's do something a little bit more than a square. A hexagon. Try and do a hexagon. My circle's not good, so. You already said hexagon.
I meant it to be a friend.
Well, I already drew 6
It's
points.
okay, it's
Okay. So, for any regular polygon, we need to show the exact same thing. That it is circumscribed in exactly one circle. Right?
Yes.
Okay. So here's the way that we're going to start it. We're going to say take any 3 consecutive points, A, B, C, and then those 3 points give us a triangle.
Right.
And we already showed that there's one and exactly one circle that circumscribes a triangle. Now we need to show that the same circle also gets this point, this point, and this point. Okay? So we've got the circle that circumscribes this triangle. We're going to prove that that also catches the point D. And then the way that we show captures the point D, you could also show that it captures E and F and G and H, etc. Okay? So pretend that what we're given is, given a regular polygon, prove that there's one and only one circle that circumscribes it. How do we do that? We take the first 3 points on the regular polygon. Regular polygons start with triangles. And so, there's going to be at least 3 points. There could be more. So you take the first 3 points, take the circle that circumscribes that triangle, and we're going to show that circumscribes the whole thing.
Okay.
The way we're going to do that is we're going to show that it also gets point D, but then you could also show that it gets every other point. Okay. So that's big picture what we're doing. So we say let the blue circle be the circle that happens to circumscribe these 3 points with this point O as the center of the circle. Good? Big picture, what are we trying to show? We're trying to show that this distance is equal to one of these distances, doesn't matter which one. Because we already know that these 3 points are all the same distance from here, right? Now we need to show that this is congruent to one of these. Okay. Regular polygons are equiangular and equilateral. So remember the information that we have to work with here. I know that this side length is the same long as this side length is the same long as this side length. Maybe I'll get rid of this length for now. You know how we got the triangle, right? So I know that those side lengths are all equal. And I know that this angle and this angle and that angle and that angle and that angle are all congruent since it's equal angular. Okay? So the idea here is to show that, maybe I shouldn't have erased it, maybe I'll do a dotted block line. The idea is to show that this triangle, dot, 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 that we started with, is congruent to this triangle. And then if it's congruent, oh, that doesn't give it to us. No, that's not what we want to show. Let's see.
You just
I want to show that
the
this
sides are the
triangle,
same.
COD, is congruent to one of these
Yeah.
other triangles.
CFE.
So, let's see what I want to argue real quick. First thing I want to argue is that, now remember I also know that this distance is the same as this distance is the same as this distance. I'm trying to prove that this distance is also that, right? Because those are radiuses of the circle that inscribes that
Yes.
triangle. Good? So I know that this triangle is congruent to this triangle.
Yeah.
Right? So I know that this angle is congruent to this angle, is congruent to this angle, is congruent to this angle. Right? Now this pink angle is the sum of those two. This pink angle is congruent to this pink angle, so this angle has to be the same big as that angle. You see where that comes from?
Yeah.
So that angle has to be the same big as that angle. Because pink is the sum of two blues. Pink is the sum of two blues here. So that pink and that pink we already knew has to be the same size since it's a regular polygon. So we get that angle is the same big as that angle.
Yes.
Right? Now that angle, side, angle, it's congruent to either one of these. We have side, angle, side. Sorry, I said angle, side, angle. I meant by side, angle, side. This triangle is congruent to this triangle.
Yes.
Therefore, this side is the same big as that side. And that's how you show it. That means that D is on the circle because its distance from O is the same big as that. Because we started out with a circle that had these 3 points on it. Did you follow all that? It's kind of a messy picture, but the idea is not that hard if you see it. Do we need to redo it?
Nope. I got it.
Do we need to redo it? Yeah? No? Yeah? You think you could draw it out and do it yourself?
I understand the idea.
What's the idea?
The idea is first you begin with the triangle.
A, B, C.
Yeah.
Create a circle that circumscribes
Yeah,
it.
you create the circle with that.
So then you have O. When you have that distance the same as that distance is the same as that distance.
Yeah. And then
And then you show that this triangle is congruent to this triangle. Right? Good. So you see the process. Okay. That's that theorem. That was theorem 11.2. Theorem 11.3 is tangents to circles. Have we already defined what a tangent is?
Yeah.
Do you know what a tangent line is?
You did what?
You have not described what a tangent line is.
What is a tangent line to a circle?
No, we talked about it and we decided to skip over it.
Yeah, we talked about it. We know what a tangent is. A tangent is a line that only meets one point to the circle.
Right, that's exactly what it is. So a tangent line to a circle is a line that only intersects it at one point.
Yes.
Notice that's a very special line. Because
Yeah,
most
it's
lines
just-
would either, you'd think would either miss it or go through 2 points.
Q's wouldn't be alive without tangent lines.
What would it be?
What?
Q's? What's a Q?
That is not
The
true.
letter.
What?
It's a line
That is not a tangent line.
One point.
Because if we think about the line,
Oh.
that intersects it twice.
How does that work with?
Yeah, tangent line is a special line. It's one that looks like this. And you say, wait, does it really only go through 1 point? Couldn't you zoom in closer and closer and closer and it actually goes through 2?
Yeah.
Really, it just goes through just 1 point. Tangent lines are a special line. They're a line that only goes through 1 point. So, let's look at theorem 11.3. If OP is a radius of a circle with center O and the line L passes through P and is perpendicular to OP, then L has exactly 1 point in common with the circle. Oh, they don't even mention that it's tangent. Where did they get tangent? Oh, it's in the heading of the section. So let's prove that. 11. One of you guys just want to read to me?
Yes.
All right, yeah.
Okay, if OP is the radius of a circle with center O, and a line L passes through P, and is perpendicular to OP, then L has exactly 1 point in common with the circle.
All right. So make sure you understand that. If OP is the radius of a circle with center O, and a line L passes through P, and L is perpendicular to OP, then L intersects the circle at exactly 1 point. So, let's draw out a picture real quick and figure out how to prove this. Here's O, here's P. Well, here's our radius, and we've got L is perpendicular to OP, so this is a right angle. Prove that L intersects at only P. So we're going to do this by way of contradiction. One, by way of contradiction. Maybe I'll walk through a big picture. Maybe I don't need to actually prove it, just go through the picture. So here's the way that we prove this. We say, let's assume by way of contradiction that there is secretly some other point, call it A, where this line intersects a circle. And maybe A is really close to P, right? So maybe if you zoom in far enough, that does actually go through 2 points. So if A goes through it, and then we're assuming that there is secretly some other point A where L intersects a circle. Now this is an impossible picture. We're doing a proof by contradiction. Assume that there is more than 1 point where L intersects the circle. Okay? So that A is secretly another point on the circle and it's on L.
Why is it?
That's why we're proving.
We're going to show that this is an impossible picture. So let's assume that it's true and show why that can't be true. Now, if A is on the circle, how far is it from A to O?
It's the same distance as OP.
Right. Then this distance, then we get the distance OA is equal to the distance OP. Why is that impossible?
Because it's on the circle.
Hippopotamus.
It's on a circle, and it's not perpendicular.
Why do I know that this distance being equal to this distance is a big no-no? Not a chance, Nancy. No way.
Two radiuses. It's 2 different lines that you said.
Okay, because that's
So I'm drawing a right triangle, and this distance is 2, and this distance is 2.
Oh.
Why is that impossible?
because of the
It is.
Pythagorean theorem.
By the Pythagorean Theorem.
What's the Pythagorean theorem?
The square of this distance is the square of this distance plus the square of this distance. The only way that this equals this is if this has a distance of 0. Or in other words, it's not a triangle. In other words, A is also right there where P is. Right? That distance being the same as that distance? No. No chance. No chance. Does that make sense? Why that's an obvious contradiction?
Yes.
Yes.
Why there's 4 exclamation points? That is excessive.
I
Sorry.
think you needed that one.
They did too. There's easy. So I think we got at least 3.
I don't know. 3 just seems like the right number that you do. You do 1 or 3.
That's weird.
So are you.
It's because no one can
Keep you
turn
around.
your angry writing into a smiley face if you do 3.
Yeah, of course.
Yeah, but
That
it
is
is 4. Maybe you should do 4, because if you make 2 spices.
You don't want people to be able to do
You
that.
don't want it's angry.
You want it to stay angry. You don't want it to be a happy message.
You
It's
can
an
do
angry
faces
message.
with the nose.
His nose is right between their eyes.
Look at that one though. It's kind of lower.
Okay. Let's do the converse of this. What's the converse of a theorem?
I forgot what converse was.
It's proving it going the opposite direction.
Right. So now we want to prove. So if I have a statement, A implies B, what's the converse of that?
B implies A.
B implies A. So what's the converse of this theorem?
L intersects the circle at exactly one point if OP is the radius of the circle with center O and a line L passes the B. L.
Point 1 exactly as circle that intersects L.
Yeah.
So we're going to do the converse of this. We're going to say, if you draw a line that intersects that circle at exactly one point,
And P
rest of
always
that.
perpendicular.
And the rest of
Then
that.
that point is the radius of the circle.
let's state it in simpler terms. A line tangent to a circle at a point P is perpendicular to the radius containing P.
You were doing
Right? So now we need to show that if we have O here, and we have some point P here, and if we have a line that goes through P, and only goes through P, then it's going to be perpendicular to this. So here's OP. If I have a tangent that goes through P, then it's going to be perpendicular to that. Okay? And the way that we're going to prove this is using contrapositive. What's contrapositive? So we're doing B implies A, but now we want to prove that with the contrapositive. How do we do that?
If not, then A, then not B.
Right, not A implies not B. So we're going to show that not A implies not B. Okay?
Okay.
So what was B implies A? B was a line tangent to a circle. If you have a line tangent to the circle, then it's perpendicular to the radius at that point. We're going to show if a line isn't perpendicular to a radius at that point, then it's not a tangent to the circle. Do you remember how these two things say the exact same thing?
Yes.
Is that obvious to you, or should we write that out real quick? Okay, let's write it out real quick. We have statement A and statement B. How many combinations are there?
4.
4. What are they?
True. True. False. I mean true. False. False. True. False. False.
Right? And then,
B implies A.
really quick, we'll do not A and not B. False, false, true, true, false, true, false, true. Okay, so here we're going to write B implies A. B implies A, so let's see. B implies A, true implies true?
True.
True. False implies true?
That's true implies false. Oh.
B implies A.
True.
False implies true?
Yeah.
Okay. True implies false?
No.
No. False implies false?
Yes. Yes.
Okay. Good job.
Alright.
Alright. And now, not A implies not B.
False implies false.
False implies false?
True.
False implies true?
True.
That's false.
It's true.
Oh, 4 twice in a row.
True implies false?
That's
False.
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 True implies true? Remember, false implies
Ah, you said it.
false implies anything is always true.
I was looking
It's
at the
vacuously
implies A.
true.
I got confused.
Okay. This is what we call a vacuously true statement. If Donnie is a giant elephant, then he's king of the world.
True.
If Donnie is a giant elephant, if I ever start any statement that way, it's always true. It's not false, so it's true.
Would you bow to a giant elephant?
All right. So now compare true, true, false, true. Ta-da! Contrapositive.
That's so dope. I love using,
What? I'm getting.
what do you call this? Different versions of saying the same thing.
That's a lamp.
I'm not sure what you mean.
Like a contrapositive.
Logically equivalent?
Logically equivalent of implies.
Yeah, did I already show you that logic problem? The da and ta one or whatever? The one where you ask the three gods, talk to the three gods,
Yeah.
and then the tautology that you have to create to prove it. Do it. The one I
You
created.
didn't show me it.
Oh, I can show you it pretty easily.
Oh, maybe you didn't text it.
Alright, so we're going to show the contrapositive. We're going to show that if I have a line that's not perpendicular to the radius, then it intersects at 2 points. Okay? That's what I need to show. That's the contrapositive. So, let's start with that. So we have L, and it is not perpendicular here. Since it is not perpendicular there, then I can draw a perpendicular line to this line. That's different from here, right?
Yeah.
Now how do I know that this point is inside the circle? How do I know it's not secretly out here?
Oh, because
Because of
like
that line.
This is the hypotenuse of the circle.
Yeah.
It's the longest distance on the circle, or on this triangle. So this is less than this. It's a point whose distance from O is less than the radius. Therefore, it's on the interior of the circle.
Yeah.
Okay? So I pick the point that if you draw the perpendicular line through that point, it goes through O. And that has to be interior to the circle. Okay? Now, I just make a congruent triangle. So that this is the same as this.
OP.
Now, this distance, we'll call this point A, I guess. This distance is the same as this distance, right? Therefore, A is on the circle, and it's on L. So how did I get A? I say, here's P. I say, from this point, construct a point A so that this segment is congruent to this segment. And then with that segment and the fact that that's a right angle, I know that this triangle is congruent to this triangle. See how you do that? Pretty easy. So easy.
Yep.
So, if a line is not perpendicular, then it intersects at not exactly 1 point. So, if it intersects at exactly 1 point, then it's perpendicular.
What's B again?
So, B is tangent, A is perpendicular.
So, if a line is perpendicular to OP, then it's not tangent to the circle.
If a line, so we started with, if a line is perpendicular to the radius at P, then it's tangent. Then we want to show if it's tangent, then it's perpendicular. The way we showed that is if it's not perpendicular, then it's not tangent.
Okay. So if it's not perpendicular, meaning it is perpendicular, then it is.
We never did a double knot.
Okay, but
Are you saying take the contrapositive of the
I'm
contrapositive?
trying to make a vacuously true statement out of the contrapositive. False, false.
Okay. intersects a circle at 8 points, then it's tangent to the circle. Or then it's perpendicular to whatever. Say whatever you want. Which is kind of an impossible thing. The line can't intersect a circle at 8 points. It can only intersect at 1 or 2 or none. Alright. Anyways, so there's theorem 11.3. Oh, that was 11.4. We did 11.3 and then we did its converse.
Oh, yeah.
They did definition.
Oh, did I skip the definition?
Point of tangency.
11.3 and 11.4.
Oh.
They did 11.3, said, hey, that's tangent.
A line L is tangent to a circle if it has exactly one point in common with the circle.
We did that.
The point is called the point of tangency. Okay, so you know what a tangent line is, and then the point of tangency is where the tangent line intersects a circle.
Okay.
So when we were doing it, P was our point of tangency, and L was our tangent line.
Yeah.
Good? You look tired. All right. Next, definition 11.3. A circle is said to be inscribed in a polygon if it is tangent to each of the sides of the polygon. All right. So a circumscribing circle. Let's try and draw both these. Oh, this is going to be weird. My artwork is going to be terrible.
We know that.
But I'm going to try and do it. So let's do it with a square. That'll probably be easiest. So if we have some regular polygon, then a circle that goes through all the vertices
Doesn't
is
say regular polygon.
a regular polygon.
Oh, is this from before?
We're doing both of them. Oh, does the definition not say regular?
Well, that has to be regular, right?
It's taking a circle inside of a polygon. Not.
A circle, I know, I'm showing both circumscribed and inscribed.
Oh, okay. And it doesn't say regular polygon.
Oh,
The circle inscribed.
okay. Well, we'll talk about both of them. Maybe pick a different color for this one. Okay. So if I have a polygon, namely the square, the circumscribing circle is a circle that goes through all the vertices. The inscribed circle is a circle that is tangent to all the lines, all the sides. So we have our inscribed circle is a black one, our circumscribing circle is the blue one. And tangent, 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 tangent. Does that make sense?
Yeah.
Yep.
Alright. And then theorem 11.5. There is a circle inscribed in every regular polygon. So we showed that a circle circumscribed every regular polygon. Now we need to show that there's a circle inscribed in every regular polygon. So how do we want to say it? What's the verbiage?
There's
It's a
this
circle.
Oh, what number is this?
inscribed in every-
11.5. There is a circle what?
Inscribed in every regular polygon.
Inscribed. Let's see. In every regular polygon. Okay. So, what kind of regular polygon should we start out with for our picture?
A square.
Square. Let's do more sides than that.
Let's do a polygon.
A polygon. Ah, thank you. Maybe we'll do our hexagon again.
Yeah, I like this better, please.
Oh well, not gonna be good. Not an artist. So we have some regular polygon, and we need to show that there is a circle inscribed in it. Now we already have for free that there is a circle that circumscribes it. We already proved that. So I know that I have a circle that circumscribes this thing. Should have drawn my circle first, come to think of it. That was terrible. Whatever. Good enough. So we have that circle with center O. Probably making this picture too small. That was theorem 11.2. So by theorem 11.2, we already know that there is a circle that circumscribes this thing with this center O. Okay? We need to show that this point how actually do we want to show this? Show that it's inscribed, we need to show that it's tangent to all the sides.
But if you show if it's tangent to like 2 of them, then you know it's tangent to all of them, don't you?
Let's see how they go about doing this. There is a circle inscribed in every regular polygon. Let O be the center of the circle circumscribing the polygon. Let AB be a side of the polygon. And C the midpoint. And then they're just going to construct a perpendicular bisector. Oh, I guess here's the way you can think about it. We're going to pick 2 arbitrary sides. Doesn't matter which 2 sides, 2 adjacent sides. And we're going to show that both those sides are adjacent. Or sorry.
They are adjacent.
We're going to show that
The smaller circle touches.
we're going to construct a circle that goes through the midpoint here and show that it also goes through the midpoint here. And by same argument, you can show that it also goes through the midpoint there, to the midpoint there, to the midpoint
It
there.
goes to the midpoint?
The bisector.
Yeah. So I'm gonna pick a point here, and I'm going to draw a circle with this as its center, the same center as the big outside circle. And I'm going to draw a circle with this as its radius. And I'm going to show that that circle also happens to go through a point here. And then by the same argument, if it goes through a point here, it goes through a point here, you can say if it goes through a point here, it goes through a point here, if it goes through a point here, it goes through a point here, etc. So that's the big picture of how we're going to do it. So I'm going to start by constructing a circle with this as its radius. And then I need to show that this midpoint is also on there. So I'm going to pick the midpoint there. So I know that this distance is the same as this distance, right? And then I need to show that this distance is the same as this distance, where this is also the same as that. Okay? And you might see right out the door already how we're going to do this. Because I constructed the outside circle, I have this length is the same as this length, is the same as this length, because those are points to the outside circle. So that is the same as that, is the same as that. And now I can easily show that this triangle is congruent to this triangle is congruent to this triangle. Do you see how to do that? Should we walk through it? Let's walk through it. Okay. Let me start out with a bigger picture now, and then we'll do this again. So really we would start with regular polygon, but I'm going to draw a circle first and then draw the polygon, just because it's easier. So that's going to be my circumscribing circle of my regular polygon. My regular polygon, we're going to do a hexagon. So pretend we started out with the hexagon. Step 1 was construct the circumscribed circle, which we proved existed already. And we call O the center of that circle. You with me?
Yeah.
Step 2, pick any line segment you want, any side you want, doesn't matter which side. We'll use this one. Find its midpoint. So that those 2 segments are the same. Using this as a radius, construct a circle. Claim that circle contains the midpoint over here. So this point is also the midpoint of this segment. It's a regular polygon, so this is the same long as this. So that's the same as that, it's the same as that, it's the same as that. So we're claiming if we draw a circle through with this radius through this point with this as a center, it's also going to hit that point. That's our claim, that's what we need to prove. Now we know that this distance is the same as this distance is the same as this distance. Those are distances from the center to the outside circle. Those are all radiuses of our big circle. So we've already got all those distances are the same. We have, let me see, we have by side, side, side that this is congruent to this.
Yeah.
By side, 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 these two triangles are congruent. Therefore, we have that this angle is congruent to this angle. Oh, we already had that because we have an isosceles triangle. Let's see. Side, 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 thank you. Side, 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 we have this big triangle is congruent to this big triangle.
Yeah.
So this angle is also the same as this angle, right? Yeah. Now construct this line. This triangle is congruent to this triangle by side equals side.
So the same.
So this side and this side are the same length. Therefore, this point is on the circle with this as its radius. And then we can do the same thing to get the point here, 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 and all the sides.
Right.
That make sense? Okay. That was theorem 11.5. Two regular polygons are similar if and only if they have the same number of sides. Okay. That one's kind of obvious, but we'll go over it. Now remember, what does it mean for two regular polygons to be similar? Oh, I did? What definition? 11.4. Oh, the center of a regular polygon is the center of its circumscribing circle.
Of the inscribed
Or inscribed. Inscribed and circumscribed, remember they ended up having the same point. Probably should have made that more clear when we had the picture up here, but they both had O as their center.
Yeah.
So when you have a regular polygon, the inscribed circle and the circumscribed circle have the same center, and we also call that center the center of the regular polygon. And then the apothem is the radius of the inscribed circle. So we call the radius of the polygon, now I won't bother with a really nice picture, but we'll just do something real quick. So we've got some regular polygon inside here. That's regular, that's a square. And then we have an inscribed circle. Okay? And then O is the same for all of them. O is the center. The distance from here to the circumscribing circle is the radius, and the distance from here to the inscribing circle is the apothem. Yes. So that's a
Wait, what's the one called again?
radius, apothem.
Okay.
Make sense?
Yeah.
Yep.
The angle between two adjacent vertices is the central angle as well.
Oh. And then you take any two adjacent vertices. So this vertice is adjacent with which vertice?
That one and
That one or that one. Take two adjacent vertices and then construct their angle with the center point, and that is called a central angle. So if I have some regular hexagon, and I want to construct a central angle that uses the center of the circumscribing circle and two adjacent vertices. So this vertice, and that, there's a central angle.
Is the central angle
called a central angle. It uses the center of the circle and two adjacent vertices. So let me read through that verbatim one more time, make sure we covered everything. The center of a regular polygon is the center of the inscribed or circumscribed circle. The apothem of a regular polygon is the length of the radius of the inscribed circle. The radius of a regular polygon is the radius of the circumscribed circle. A central angle of a regular polygon is an angle with vertex at the center, whose sides contain adjacent vertices of the parallelogram. Here's two adjacent vertices, and sides contain those two vertices.
Why do they have to be adjacent vertices?
This is not a central angle.
Why not?
It's a definition.
Yeah, but
That's like asking why do we call this a square?
Okay. Hey, look, it's a cube.
It's a definition. Yep, it's a cube.
It's a hollow box.
Yep, it's a hollow box. Open right there.
Yeah.
All right. Okay, silence vocabulary. What's the apothem?
It's
Small
a.
radius.
I don't really
It's
care.
the inscribed radius.
We are going to care. That word's going to keep coming up, so I want to make sure you understand it.
So it's when you don't really care.
It's like from the center.
It's the
to
inscribed radius.
The inscribed radius. No, it's not.
It's the radius of the inscribed circle.
So the inscribed.
We don't know what inscribed radius is.
It's also touching the regular polygon.
Well, the inscribed circle has a definition, and it's a circle that's tangent to all the sides of the polygon.
Right, but you could have.
Then it has its
put
radius.
spot where it didn't. So it's got to be the center.
No, because it's just a number. A radius and an apothem are just a number.
Thought it was a line.
No. We sometimes draw a line segment to represent the radius of the circle, but the radius is just a number. It's just a distance, and so is the apothem. In fact, it probably specifies that.
Yes.
That is a number. Yeah. Good point. Okay. Now, let's go over regular polygons. Not regular polygons. Similar polygons. What do we mean when two polygons are similar?
They are.
You have the same.
They have the same number of sides.
So, are you telling me that this polygon and this polygon and this polygon are all similar?
Yes.
No,
No.
they are not.
They're similar if they have
Oh, they have to be
same
regular.
measurement
They have to be
angles.
regular.
Their angle measures have to be the same,
And their sides have to be proportional.
and their sides have to be proportional. Here's why you can't just say their angles are the same, otherwise these two are similar. We want this thing to be similar with something that looks like this. Right? Roughly?
Yeah.
Because all its side lengths are proportional. In other words, this length over this length is equal to this length over this length is equal to this length over this length is equal to this length over this length. And that angle is congruent to that angle is congruent to that angle is congruent to that angle.
Yeah.
That's what we mean by similar. All the sides are proportional and all corresponding sides. Remember, order matters when we're saying two things are similar, just like when we say two things are congruent. So corresponding sides are proportional and corresponding angles are congruent.
Yeah.
Good?
So all sides of a regular polygon, the ratio is 1:1.
All sides of a regular polygon.
The ratio is 1:1.
I don't know what you mean by that. Anyways, so now this thing says, prove that for any regular polygon, if two regular polygons have the same, which way is it? Let me get my direction right.
If and only if.
Oh, it's an if and only if. So me getting the direction right doesn't matter. Okay, two regular polygons are similar if they have the same number of sides. Let's do that one first. Two regular polygons are similar if they have the same number of sides.
That makes sense.
It does make sense, but now let's prove it. Let's see if he gives like a... Oh, let's read his preliminary remark before we do the proof. Recall that two polygons are similar if there is a correspondence between their angles and sides such that corresponding angles are congruent and corresponding sides are proportional. Thus, if the polygons are similar, they necessarily have the same number of sides, and the only if part of the theorem is obvious. Therefore, we have only to prove that if they have the same number of sides, they must be similar. So, we need to prove, in other words, if they're similar, they have the same number of sides. Now we need to prove if they have the same number of sides, they're similar. You see how it's obvious that if they're similar, then they have the same number of sides? How can they have corresponding sides proportional if they don't have the same number of sides?
Right.
So if they're similar, then they have the same number of sides. All we need to worry about is if they have the same number of sides, then they're similar. Okay? And we're going to do proof by contradiction. Is that how we want to do this, or do we want to use contrapositive? Let's see his way of proving it. Proof. Suppose two regular polygons have consecutive vertices that and that respectively. Suppose also that they are not similar.
Yeah,
Okay. So, let's see. Since they are regular, then the ratio of all their sides is automatically going to be the same. That doesn't change. So now we need to handle the angles.
Wait, what?
Maybe draw a picture real quick. So let's pretend that we're talking about, geez, that was a terrible marker.
I was confused why you need to deal with angles.
Why we only need to deal with the angles?
Yeah.
Because the sides are all equal.
Oh, so
regular
therefore they already are.
So, in other words, so here's a square,
Therefore they would already be
here's a pentagon.
proportional.
Since that side's the same as that, same as that, same as that, same as that, and that's the same as that, is the same as that, is the same as that, then this distance over this distance is going to equal this distance over this distance, is going to equal this distance over this distance, etc. Because you're always talking about the same side lengths,
Okay.
right? If we say that the side lengths of all this thing is x, and the side lengths of all this thing is y, then it's always x over y. X over y equals x over y equals x over y.
Okay.
So now we need to show that their angles, so it's not necessarily that the sides aren't proportional, it's that their angles might not be.
But their angles aren't supposed to be proportional. They're supposed to be congruent.
Or congruent, that's what I meant. So let's read the direction that we're proving when we're done. We are proving that two regular polygons are similar if they have the same number of sides. Wait, then we're doing it by contradiction, right? Let's see. Suppose that two regular polygons have consecutive vertices that, respectively. Suppose also that the polygons are not similar. Okay. So if they're not similar, then they're not regular, I guess is what we're going to prove.
Then the angles.
Oh, then they have different number of sides is what we're going to prove. Right? I don't know. Is he doing a proof by contradiction? He doesn't really state what he's doing.
Well, he does, the sum of the angles is not congruent.
Therefore, we have only to prove that if the number of sides, if they have the same number of sides, then they must be similar. Suppose that two regular polygons have consecutive vertices that and that respectively, as in figure 11-8. Okay, so we're not talking about two ones with different number of sides. So they have the same number of sides. So we have two with the same number of sides. Do. Okay. Since they're regular, then we automatically have that the proportion of their sides is going to be the same. In other words, that distance over that distance is going to equal that distance over that distance, etc., because we're always talking about the same distances.
Right.
Oh, okay. We are doing proof by contradiction. We're proving if we have two triangles with the same, two regular polygons with the same number of sides, then they're similar. He's going to say, assume by way of contradiction that they're not similar. Okay? First off, their proportions have to be the same. So the only way that they're not similar is for their angles to be different.
Yes.
So now we're going to show it's impossible for their angles to be different. So let's write that out. Yeah, he doesn't explicitly say that he's doing a proof by contradiction. That's why we got lost for a second. So what number is this? 6. If two regular polygons have the same number of sides, then they are similar. Okay, so we assume by way of contradiction, they are not similar. Alright. I'm not sure how to say this next part. I want to say observe that the proportion of the sides is always the same. Right? Because the side lengths are always the same. What's a good way to say that?
Observe that the portion of the sides are always the same because the side lengths are the same.
I don't know, I like that word. Observe that the portions of the sides are always the same since they're regular. Probably a better way to say that. Same since they are regular. Okay. So then the angles have to be different. 3. Then I don't want to write out a full proof of this because I didn't label points. I need to specify. So let me just talk to you and tell you where we get our problem. The theorem that we're going to use is, if you remember last time, you remember how we showed that the sum of the exterior angles always adds up to 2 straight angles?
Yes.
Do you remember doing that? So, huh?
Were we not talking about the last one?
I don't think it was last time.
It was last time.
It was last time?
Because it was in here.
It was in my lecture? You sure you didn't watch
Or it
2
was
lectures
2
back
weeks
to back?
ago.
Yeah, I think it was 2 times ago.
Yeah.
Do you know what I'm talking about? The sum of the exterior angles is 2 straight angles. Do we need to go over that real quick? It doesn't take much to show.
Yeah.
So if you're not sure, let's just show it.
I
With
remember.
the outline. The outline.
Let's look at it real quick. So we've got a triangle, right? And let's look at its exterior angles. That's this angle,
Yeah, I was gonna.
this angle, and this angle.
That's wrong.
The
Did it weird.
up and this angle, right?
Yeah.
Now, this whole thing plus this whole thing plus this whole thing is 3 straight angles. The sum of the triangle is 1 straight angle, so that leaves 2 straight angles for the outside. Do you see what I'm saying? Let's see. Do doubles real quick. That angle plus that angle plus that angle is 1 straight angle, right? The sum of the angles for a triangle is 1 straight angle, 180 degrees. So do we need to start with that proof?
Just go with it.
No, we can, if that doesn't make sense, let's do it. Triangle. Draw any triangle between two parallel, for any triangle I have, I can draw two parallel lines like that for the triangle, right?
I remember.
So then, this angle is the same as this angle. This angle is the same as itself, and then this angle is the same as this angle. So the sum of the angles of a triangle is a straight angle, right? So the sum of the angles of a triangle is a straight angle, right? And then this angle, this whole angle is one straight angle. This whole angle is one straight angle, and this whole angle is one straight angle. So we have 3 straight angles. We have one on the inside, so we have 2 straight angles on the outside. In other words, that plus that is 2 straight angles. Because there's 3 total and one's on the inside. So there has to be 2 on the outside. And we could do the exact same argument for any one you want to talk about. We'll just show a square and then I think you'll get it. If I have a square, let's look at its exterior angles. That means we're talking about this angle, this angle, this angle, and this angle. Now that's 1, 2, 3, 4 straight angles. So we have 4 straight angles total. And then a square is composed of 2 triangles. So it has 2 straight angles on the inside. In other words, this angle plus this angle plus this angle is one straight angle, and this angle plus this angle plus this angle is another straight angle. So we have 4 straight angles when we talk about this whole thing plus this whole thing plus this whole thing plus this whole thing. And then minus that portion of this one, that portion of this one, that portion of this one, and that portion of this one leaves us with 2 straight angles. And then you can continue for a pentagon, a hexagon, etc. So the sum of the exterior of any regular polygon, the sum of the exterior angles, is always 2 straight angles. So that's starting to click back in your memory some? Okay. So, if I have these 2 regular polygons, not necessarily 5-sided, but 2 regular polygons that have the same number of sides, and we assume that they're not similar, well, their sides are proportional for sure, so the only thing that remains is that their angles must be different if they're not similar. And we're going to show that's impossible. Here's how. That means either this thing's angles are smaller than this thing's angles, or this thing's angles are smaller than this thing's angles. One of those 2, right?
They're regular, so all the angles.
Because they're regular, so all the angles are the same. So we know that this angle is the same as this angle, is the same as this angle, is the same as this angle, is the same as this angle. And we know that this one's the same as this one, is the same as this one, is the same as this one, is the same as this one. So either all these angles are smaller than all these ones, or all these ones are smaller than all these ones, if these things aren't similar. Well, if all these ones are smaller, then their exterior angles must add up. How can I say this right? So thinking about this thing, one of these things' exterior angles, let's just do one of them. Right? If this angle is smaller than this angle, then its exterior angle, this one, must be bigger than this one's exterior angle. Sorry, I should use different things. 3 and 4, I guess. If this angle is smaller than this angle, then its exterior angle is bigger than this one's exterior angle. So when I sum up its exterior angles, I'm going to get a bigger number than when I sum up its exterior angles. But the sum of the exterior angles is always 2 straight angles.
Right.
Contradiction. Do you see how you get the contradiction? It's based in the fact that for any convex polygon, which regular ones are, the sum of the exterior angles is always 2 straight angles. This one has 5 exterior angles, this one has 5 exterior angles. If all its exterior angles are bigger than all its exterior angles, it adds up to a bigger number, and not the same number. They have to add up to the same number. they have to have two straight angles. Does that make sense?
Yeah.
That's how the contradiction comes out. And I don't want to write that because then I have to label all these things to talk about it. And it'll get messy. Do you see the picture? Because I can keep explaining the picture, I just don't want to write this out. Because how I started is bad. I should have labeled points. Alright. That's theorem 11-6. Theorem 11-7. The perimeter of a regular polygon with the same number of sides are proportional. The perimeters of regular polygons with the same number of sides are proportional to their radii. What does it mean for their perimeters to be proportional to their radii? Are you guys just dead right now?
Yes.
What's that saying?
The radii is
Okay.
the apophones.
It would. We can stop right here. I'm losing you guys.
I keep lots of
There's
them.
no reason to power through, and I expected to finish 11 next week anyways. I just hope to get to limits first. And then stop there. Huh? What are limits? Maybe we'll just talk briefly about limits. Huh?
What?
Before you can understand what a limit is, you first need to know what a set is. You know what a set is?
You taught us like the squirrely thing and then the zero.
Yeah, that's how we represent it. We use these things. There's a set containing 1 and 2. Here's another set. Are those two sets the same?
No. Yes.
No.
What's the size of this set? That's like the one answer right there is fair. Well, I guess no. What's the size of this set?
4.
Okay, so here's what a set is. A set is an unordered, unique collection. So what do we mean by that? Order doesn't matter, and then repeating elements doesn't matter. So this set is actually equal to this set is actually equal to the set 2, 1.
So it is equal.
Order doesn't matter, and repeating elements doesn't matter.
Okay.
So it is. So I was right.
Yeah, so those two sets are the same set. So that is what a set is. Now, have you ever learned what a function is?
Yes.
What's a function?
There's a set that goes in and there's a set that comes out.
In and out of what?
So there's a
It's a
set
factor?
that equals another set.
A set equals another set, so this is a function.
No.
The function's 1.
Function 1?
It functions
All right.
yeah.
Here's what a function is. A function is a set of ordered pairs. Sorry, I should have talked about lists before we talked about set or ordered pairs. So here's sets. Another concept that we have are, we call them lists or we call them tuples, or if there's only 2 of them, we call them an ordered pair, and we represent them with rounded brackets. So 1, 2 is not the same thing as 2, 1 is definitely not the same thing as 2, 1, 1, 2. Those are all very different. So we call these things lists or tuples. Order matters here, repeating elements matter here, and we call it an ordered pair when there's only 2 of them. So people often say an ordered pair, here's what they're talking about. They're talking about 2 things where the order matters, and there's exactly 2. So a function is a set of ordered pairs there's a function.
I totally thought I was hallucinating.
A robot wants to be Harry Potter.
A function is a set of ordered pairs, doesn't matter what those things are, but they're in an order where every unique left-hand element goes to a unique right-hand element. In other words, the same thing's not mapped to two different things. It'd be easier to show you how I make this not a function. Right now this is a function. If I add a comma b, is this still a function?
Yeah.
Yep, still a function. But now if I do a comma c, now it's not a function. Because a goes to b and a goes to c. Can't have that.
Okay.
This is when it becomes a function. Or this is when it becomes not a function.
Alright.
So a function is a set of ordered pairs such that every left-hand element only goes to, every unique left-hand element only goes to one right-hand element. Right? If I would have made this CB, so we have A going to B and C going to B, we're fine.
Because it matters what the left hand
Yeah.
is going to.
Every left-hand element needs to go to only one right-hand element. Doesn't matter if the same right-hand element goes to two different left-hand elements, but every left-hand element needs to go to the same right-hand element.
Okay.
Does that make sense? So that's a function.
Okay.
You're used to seeing functions like or sometimes, because we're so in love with our graphing, we do y equals x squared. But you're used to seeing a function like this. How the heck is that a function if a function is a set of ordered pairs?
Because there's a left that goes to the right.
This is syntactic sugar. This is shorthand for writing an infinite set. What this really represents is, and we can't write it all because there's infinitely many of them, but one of the things in there would be 1, 1. Another thing in there would be 2, 4. Another thing in there would be 9, 81. Another thing in there would be 1.5, 2.25. And it has infinitely many elements in it. We can't write them out. So we use this shorthand where we say the thing on the right-hand side is the square of the thing on the left. How do you get your right-hand side element? You do this to the left. Take your left, square it, you get your right. Take your left, square it, you get your right. Take your left, square it, you get your right. Take your left, square it, you get your right. So this is just shorthand for writing this infinite set. But a function is a set of ordered pairs. Okay? Now, we have a special type of function, which we call a series. A series is a function where the left-hand element is always a natural number, and it counts up through the natural numbers.
Right.
So, a series would be like, 1's our first natural number. I don't remember if this book, I think this book started with 1 as a natural number. Some books use 0 included in the natural numbers, other books start with 1. Do you know what I mean by natural numbers? What are the natural numbers?
There's a word on it. 1, 2, 3, 4.
Only the whole numbers.
Yeah.
So it's either the positive whole numbers if you start at 1, or the positive whole numbers and 0 if you start at 0. Different authors use it differently. But a series is a function whose left-hand element is always a natural number, and it uses all the natural numbers, and its right-hand element can be anything. Doesn't matter. So I could have 1, A. I could have 2, Q. I could have 4, SpongeBob. I could have 3, Patrick. Can't draw a star. Looks like we're just going to put B. B for Patrick. Dot, dot, dot. Now, order doesn't matter, so it doesn't matter that I used 4 before 3. But it has to use every single natural number, so it goes on forever. It's infinitely many, just like this is infinitely many. This is an infinitely large set. A series is an infinitely large set. It's an infinitely large set where all the left-hand elements are the natural numbers, and it uses all the natural numbers.
So that one can use points, decimals, and that one can't.
It could over here. This could have been
Yeah, but the
2.9.
right or the left.
but the left-hand elements are the natural numbers. It uses all the natural numbers and only the natural numbers, then we call it a series. Or it uses all the natural numbers up to a specific natural number. Our shorthand for writing a series is often like this. This represents the series 1, 1 over 1, 2, 1 over 2, 3, 1 over 3, dot, dot, dot. We just tell you, because we already know what all the left-hand elements are going to be, we say the right-hand element always looks like this with respect to the left-hand element. When the left-hand element is n, the right-hand element is 1 over n. When the left-hand element is 1, the right-hand element is 1 over 1. When the left-hand element is 2, the right-hand element is 1 over 2. When the left-hand element is n, the right-hand element is 1 over n.
Yeah, but you can't do that with how if it becomes like a S1.
We're talking about a series.
It's only natural.
A series only uses the natural numbers. All these left-hand numbers, by the way, we call the domain. And the right-hand ones, we call the codomain.
Okay.
But the domain is the natural numbers. And we use a shorthand that tells you how to get the right-hand element for a particular left-hand element. If the left-hand element is n, the right-hand element is 1 over n. Just like if the left-hand element is x, the right-hand element is x squared. If the left-hand element is 9, the right-hand element is 81. That's what this is saying. This tells you how to get the right-hand element from the left. This tells you how to get the right-hand element from the left.
Okay.
You with me so far? Okay. Now, authors are lazy, so typically the way that they end up writing this is they just write out the right-hand elements in order. Because we just say this one is the first one, this one's the second one, this one's the third one. These numbers are just keeping track of the order that these come in. And so if we just write them in the right order, we can kind of ignore their left-hand elements. So some authors will just write 1 over 1, 1 over 2, 1 over 3, dot, 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 1 over n. Representing the same idea. So this is all ways of representing the same set. The same series. Okay? So a series is a function whose domain is the natural numbers. It uses all the natural numbers or all the natural numbers up to a certain number n. If it uses all the natural numbers, we call it an infinite series. If it only uses it up to a certain number, we call it a finite series. But it needs to use all the natural numbers up to a certain natural number. So here is one example. 1 over 1, 1 over 2, 1 over 3. That one was a finite series. Just had 3 terms. Representing that properly, all of it seems explicitly. That would be 1 comma 1 over 1, comma 2 comma 1 over 2, comma 3 comma 1 over 3. So this is what it really is. This is shorthand for writing that same thing. Because we kept it in order. So we said, this one was the one associated with the number 1, this was the one associated with the number 2, this was the one associated with the number 3, so we were on first, second, and third. Does that make sense? Okay. The idea of a limit for the purposes of this class, well, let's just talk about Convergence Series, and then we'll mention a limit. So think about this thing right here that I started writing out. 1 over 1, 1 over 2, 1 over 3. I keep on going. What number do I keep on getting closer and closer to? 100?
1.
1?
Oh.
How close is this to 1?
No, that is 1.
How close is this to 1? Halfway away. How close is this to 1? 2/3 away.
So you're getting so close.
We're getting further and further away from 1.
Yeah.
What are we getting closer and closer to? 0. Is there any number that we're getting closer and closer to than 0?
No.
What about 1 1,000,000,000th? What do we get closer and closer to? 1 1,000,000,000th or 0?
1 trillion.
Yeah, 1 1,000,000,000th. If I do this forever, do I get closer to this number or do I get closer to 0?
That number, 1 1,000,000,000.
No! I get way closer to 0 than this. Because I'm eventually going to get to the number this. I'm eventually going to get to the number this. I'm eventually going to get to this number, and this number, and this number. I'm going to keep going forever. I'm getting infinitely and infinitely smaller. I do this forever.
Okay.
Infinitely many times. No matter how small the number you think of, I will always end up being closer to 0 than that number. Wait.
What?
You starting to see it a little bit?
Yeah.
That's what we mean by this series converges. If this series keeps on getting closer and closer to a particular number, and that is a number that keeps on getting closer and closer to and no other number, then we say that the series converges to that number. We say that the series 1 over n converges to 0. Using calculus notation, there's another way we say that. We say the limit as n goes to infinity of the series 1 over n equals 0. We're saying as that number gets closer and closer to infinity, the number that this whole thing keeps getting closer and closer to is 0.
Oh.
There is no number that you can think of that it's getting closer to than it is to 0.
Okay.
No matter how small you pick, we're still going to get way farther than that. Pick as small as you want, and we still get closer to 0 than that number. Does that make sense?
Yeah.
That's what we mean by the limit of a series. It's the number that the series converges to. So as n goes to infinity, the limit as n goes to infinity of the series, we usually write series in terms of n, is 0. So let's look at another series. What about the limit as n goes to infinity of n? When does that get closer and closer to?
1 quadrillion.
At 1, it's at 1. At 2, it's at 2. At 3, it's at 3. At 4, it's at 4. At 5, it's at 5. What number does it keep getting closer and closer to?
No number.
No number. It shoots off to infinity.
Yeah.
So it doesn't diverge. Or it doesn't converge. We say that diverges if it doesn't come closer to 1.
Right.
Okay, let's try another one. What about 1 over n squared? When does that get closer and closer to? 0. We're talking about the first term's 1 over 1, the second term's 1 over 2 squared, which is 4. Then we got 1 over 9, 1 over 16,
Right.
1 over 25, dot, 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 keeps on getting closer and closer to 0. Okay. What about 6n over 6n plus 1? Let's see what that gets closer and closer to. Let's not do 6n over 6n plus 1. Let's just do n over n plus 1 for now. What does this get closer and closer to? N over n plus 1.
Yeah.
Let's start writing out some of the terms. What's the first term?
Closer to n.
It'd be 1, comma, it'd be 1 over 1 plus 1.
Which is?
2.
So 1/2. What's the next term?
2.
Oh.
2.
2/3. What's the next one?
3/4.
3/4. What's the next one?
Is 4 to 1?
4/5. Perfect. 5/6.
Oh.
6/7. 7/8.
Thanks, Mark.
Dot, dot, dot. 1,000 over 1,001. Dot, dot, dot. And the limit is 1. It gets closer and closer to 1. That's the number that it converges to.
Awesome.
That is the whole idea of a limit of a series. That's the idea of a limit in calculus. There's 4 major ideas that you have to learn in calculus. What a limit is, what a continuous function is, what a derivative is, and what an integral is. Those are the 4 things you learn in calculus, and that's one of them.
Limits in geometry.
because there's just, well, you'll see how we use them.
Okay.
But already when we were talking about area, we kept on talking about things where we were kind of using limits behind the scenes, but not really coming out and saying it.
Okay.
In other words, let's remember when we were talking about the length of a line segment. Say I'm trying to get the length of a line segment. So let's say 1, 1, and this was the square root of 2, right? And if I measure this the way that we're supposed to measure it, and you remember how you did, you marked one off, then zoomed in and went again, and marked it off and zoomed in and went again. And if you did that, you'd never stop with the square root of 2. It's irrational. You'll never get exactly there. You'll always be zooming in more and more and more.
Mm-hmm.
And so what we really meant by that's the square root of 2 is it's the limit of what you get to as you keep doing that forever. The same way that if you keep doing this forever, you eventually get to 1. There's no numbers that I can plug in that actually give me 1 here. No matter what n you pick, this isn't equal to 1.
Right.
It's just what keeps getting closer to. It doesn't matter how many times you measure it, you're never going to get the square root of 2. It's just what you get to if you keep doing that process over and over and over again. As you create that infinite decimal expansion for it, it gets closer and closer to the square root of 2. But you never actually get there. So we've kind of been hand-waving. I didn't like the way the author brought it up. I wish he would just come out and talk about limits the way he should talk about limits and then use them. Because he keeps saying that's for calculus, and he just tries sprinkling it in there when he needs it. But you kind of been using the idea behind the scenes. We just didn't come out and talk about it. So, that's the idea of a limit. We're going to be using limits. We'll probably recap some of that next time. And I'm tempted to just give you the full definition for what the limit of a series is. Just exactly the way you get it in a calculus class. Should I do it? Should I just give you a full-fledged calculus definition of a limit? Are you comfortable with absolute value?
Yes.
In fact, I can write it right now. See if you understand it. We say that 1 over n, we'll do an example to see the definition in action. The limit of this is 0. If 1 minus n 0, the absolute value of that less than some small number, any small number you pick, where n is greater than or equal to some number n. So let me now explain how this works. I say for any really small number you give me, if I can find some big n, some massive number, such that for every time I pick an n bigger than my number, then this is less than your number, we say it converges to whatever I put here. Let's see it in action. Let's see it in action real quick. Pick a small number. Pick a really small number. A really small number. We're really wanting to see, does this really get closer and closer to 0? So pick something really small. So I claim it converges to that. Pick some really small number.
1/100.
0.001. We'll do 1/1000.
Okay.
So we say, okay, you think it's 0. Can you find a number such that this series from that number on is always less than 100th away from 0? Right? We're saying the distance from 0 to this number is less than 100. That's what absolute value tells us, right? The distance between those numbers,
Yeah.
right? If I do the absolute value of this minus this, and that's a way of talking about the distance between those two numbers.
Uh-huh.
So we're saying the distance between those two numbers is less than any small number you can give me. I can find a number such that if you pick any number bigger than my number, that will be true. Okay? So what's the number I pick? The number I pick is 1000. And 1. Is it supposed to be less than or less than equal? Let's see. Doesn't matter. I'll pick 1001.
Okay.
So now I say for any n you pick bigger than 1001.
That distance will be less than the distance.
So for n greater than or equal to 1001, this distance is now less than that number.
Okay.
Okay? So for any small number you get, for any small number, if I can find an n such that for all, if I can find a big N, if I can find some massive number n, such that for all the numbers in the series after that, it's less than that distance away, we say it converges to whatever I put here. So we'll write it one more time now without hard-coded numbers. We say that something in terms of n minus our limit less than epsilon for all n greater than or equal to some n that you give me. Maybe not f of n, maybe just do my series. No, I'd use f and after that. That's the exact calculus definition. Now I didn't write out all the words, but that's what it is. So maybe we'll go over that again next time. Try and help you understand exactly what we mean by limit.
Yeah, when it's not 10 o'clock at night.
Yeah. And I don't want to go off on too big of a tangent. Maybe I shouldn't. Maybe what we were doing over here is good enough that you saw that gets closer and closer to 1. So that's the limit. Maybe that's good enough for the purposes of this class. So we'll recap it only to that extent. I won't go over the full calculus definition. All right, we'll call it good there.